So, this is a simulated result of the switching converter in both CCM and DCM. So, if you keep the duty cycle constant, so what would happen as you keep reducing the load current, the moment it enters into DCM, then what would happen? Your output voltage will start increasing if you keep the duty cycle constant. Okay, and this is what happening. If you see, this is in the CCM, and you can see there is hardly any voltage in the change in the output voltage. There is would be minor because it's simulated in the open loop. So, that is why your duty cycle is not changed. So, with the load your IR drop actually changing. So, that is why you see a very minor change in the output voltage. Otherwise, when you go in the DCM, you can see if we go from 50 milliamp to 10 milliamp, there is a significant change in the output voltage. So, it is almost like 2.7 volt or so at 10 milliamp, and although I was regulating at 0.5 volt output. So, when you go on 50 milliamp, 1 volt, and at 1 milliamp, which is a very light load, you can see 4.5 volt. So, if you further reduce, it will start approaching to VDD or Vn. Okay. Starting with the PWM modulator, and we know that switching regulator works on the principles of PWM. So, the control voltage from your feedback loop, that has to be converted to a PWM clock, which will regulate the output. So, there are three types of PWM modulator. One is your trailing edge, or basically this single edge modulation, and dual edge modulation. And this can further be divided into trailing edge, leading edge. So, we will look into more details one by one. So, if we talk about trailing edge modulation, so if this is your ramp signal, sawtooth, and this is your control voltage VCTRL, I will call it V ramp. So, now if you have a comparator, let us say you apply V control here, and V ramp at the negative, and if say PWM output is your V of PWM. So, if I want to plot V PWM, how will it look like? So, in this first region PWM will be high or low? Okay. Now let us say if we change the control voltage, it's I make it high. And one case I will take it. No. So what would happen to the PWM? In this case, it will remain high until here, okay. It will go here, okay. In the second, in this case, it will remain low, so if this is your high, it will go low here, okay. So which edge is moving here? Which edge is fixed and which edge is moving? Yeah, trailing edge is moving and leading edge is fixed. So if duty cycle is changed, then only trailing edge moves while leading edge is fixed, okay. So now let us talk about leading edge. So it should be exactly opposite of this. So if I take V ramp like this, inverted ramp, and now do the same thing. So this is VCTRL and this is your V ramp. If I want to plot BPWM, so what is happening here? Where the ramp is going? Going high, okay, which means negative terminal is going high. So duty cycle will reset here. In the previous case it was setting duty cycle was going high, here duty cycle should go low. So, it will reset here, and this is the point where negative terminal is, or V ramp is less than V control. So, this should go high. Now, change the V control again. So, what would happen at this point? Your leading edge will come here, correct? And if I have lower value of V control, then this edge will, leading edge will move here. Okay. So, which edge is moving here? Trailing edge is fixed and leading edge is moving. So, we know the trailing edge, leading edge, dual edge means both edge should move. So, what do we need to do? Combination of the two, just add the two, which means your ramp should be triangle. So, V of PWM so it will look like okay. The another case, it will remain high until here, and go low. And third case will be so this maximum duty cycle, that's why off time is reduced. As your duty cycle is increasing, which means your V control is increasing. So, you can see here off time is less, in the other case off time is stretching. So, on time will be reduced in the other case. So, if duty cycle is changed, okay. What is the advantage with this? If you are moving both the edges compared to the single edge. So, you are sampling your control signal at 2x rate here. In this case, once your duty cycle is changed, you can see here, take this case, the first case where duty cycle is around 50%. Okay. Once your duty cycle is set, it will not change for the entire clock cycle, you have to wait for the next cycle, which means once your duty cycle is changed, which is reflected into PWM, okay, and that is the point of intersection, that is where your duty cycle changes. For trailing edge, that point of intersection changes your trailing edge, here point of intersection changes your leading edge. So, that means you have to wait for next clock cycle to change the duty cycle. Here, let us say your this trailing edge is changed, after that any change in the control voltage, that will get reflected into the leading edge. So, duty cycle is basically your control voltage is getting sampled at 2x rate here. So, your sampling delay will be less compared to the previous case, and how much delay, how you model this will come to later when we look at a small signal. Okay. So, in the previous case, your delay could be as high as 1 clock cycle, here delay will be less actually, but there is a drawback with this when you change both the edges. Can anybody tell? Yeah, frequency will change, but that will happen only during the time. In steady state your frequency will recover, but during the moment instantaneous change which happens in the control voltage, during that time if both edges move, then for that particular cycle your frequency is changed. So, let us say you have a random load which is switching. So, it is quite possible that it will have a lot of harmonics in your duty cycle, frequency harmonics, which may not be good for noise sensitive applications. If you are looking, you expect your ripple to be at a fixed frequency, that may not happen in this case. So, that is why most of the time we prefer leading or trailing edge rather than dual edge.